At the bottom of the ocean, thousands of meters below the surface, the global economy relies on a physical tether resting silently in the silt. For decades, governments treated these subsea telecommunications cables as obscure commercial assets. They were planned, funded, and managed almost entirely by private consortiums, operating out of sight and out of mind. This chart graphs media and policy mentions of subsea cables alongside the term the critical infrastructure. In 2004, the line is flat. By 2024, it reaches nearly 7,000 mentions, reflecting a total reevaluation of how states view their digital security. Today, roughly 550 active cable systems transmit over 99% of all intercontinental data. That includes everything from secure diplomatic communications to the trillions of dollars in daily international financial transactions. This diagram maps the network from landing stations down to depths of 8,000 meters. Despite handling massive data loads, the infrastructure is remarkably thin. The bottom left cross-section shows the optical fibers encased in narrow insulation and armor, a tiny target in a vast ocean. When policymakers realize this vulnerability, their immediate reflex is often to apply a fortress security model. They attempt to draw lines on a map and guard the wire. But placing a naval destroyer above every kilometer of cable, or establishing permanent maritime exclusion zones across the global ocean, is physically and economically impossible. Because physical protection in the open ocean cannot scale, states are moving away from the goal of total prevention. Instead, they are adopting a structured model of systemic resilience. If you cannot stop a ship from dragging an anchor across a vital link, your digital survival depends entirely on your capacity to manage the failure when it happens. Governments rarely adopt this resilience model through foresight alone. For most, it takes a specific localized catastrophe to suddenly pull back the curtain on how much their society depends on these underwater wires. In 2003, the Boumerdez earthquake struck the coast of Algeria. This photograph captures the terrestrial destruction, but the seismic event also triggered underwater landslides that severed the major subsea connections linking Algeria to Europe. The nation was suddenly isolated. The cascading economic damage that followed provided a clear lesson in what happens when a country is abruptly severed from the global digital economy. We saw the same failure mechanism in 2022. This satellite image captures the Tonga volcanic eruption. Because the islands relied on a single cable connection, the ensuing blast caused a total nationwide communication blackout. To survive these events, experts developed the UNIDR resilience cycle. This circular flow diagram illustrates a policy alternative broken into 3 capacities: absorptive, restorative, and adaptive. The top node, absorptive capacity, is the ability to withstand a shock without total blackout, relying on engineered redundancy. This framework table breaks down regulations required to build redundancy. Under the absorptive column, governments enforce this by mandating route and landing diversity. Because companies often bundle cables to save costs, state regulators must enforce strict spatial separation between these lines. They also mandate precise cable charting. By mapping the exact coordinates of these lines for all maritime traffic, states mitigate this single most common threat to the network: commercial anchor drag. Classifying these cables as critical infrastructure provides the exact legal trigger required to force private entities to invest in these expensive physical redundancies. But no amount of spatial separation guarantees safety. Whether by nature or malice, cables will eventually be cut. The bottom right node of the cycle details restorative capacity. This phase focuses entirely on the speed of reestablishing network performance after a severance occurs. Repairing subsea infrastructure presents a unique logistical challenge. You cannot dispatch a standard terrestrial IT crew to fix a broken fiber optic line at the bottom of the ocean. This photograph shows a specialized cable inspection vessel. These are rare assets, equipped with the heavy-lifting gantries needed to locate, raise, and splice a broken line in the open ocean. The primary delay in a repair is rarely technical. It is the bureaucratic friction of securing permits to move these specialized ships through sovereign exclusive economic zones. The restorative section of the framework table addresses this bottleneck. Effective governments streamline licensing and permitting well in advance to ensure repair fleets move without delay. They also identify procurement gaps, ensuring spare supply depots are stocked with correct components before a crisis hits. States establish clear, pre-negotiated rules of engagement between naval authorities and the private repair consortiums operating the fleets. The state's role in restoration is not to physically splice the wire. Instead, it is to aggressively clear the jurisdictional roadblocks that delay private repair ships from reaching the fault. Fixing a broken cable restores the data, but it does nothing to prevent the exact same failure mechanism from striking again. The final node on the cycle diagram represents adaptive capacity. This is the process of adjusting state policy based on previous disruptions to improve the system before the next crisis. Post-crisis investigations provide the data required to update national risk management frameworks and refine domestic infrastructure policy. As shown in the adaptive column, these domestic policies scale into international relations, creating cable diplomacy. Diplomacy is essential to address vast enforcement gaps within the UN Convention on the Law of the Sea, establishing clear legal consequences for intentional sabotage in international waters. They also adapt by co-investing in technological innovation. Engineers are currently developing ways to use the optical fibers themselves as seismic sensors to detect threats before the casing is ever breached. Governments are establishing cross-border intelligence sharing protocols to track hostile actors and deter targeted attacks on deep-sea infrastructure. Adaptive capacity is the critical feedback loop. It stops governments from repeating reactive mistakes, transforming isolated disasters into systemic geopolitical hardening. Every second, an incomprehensible volume of digital data surges through dark, high-pressure environments to connect distant continents. This animated diagram maps a primary cable route. Enforcing absorptive capacity layers multiple redundant branches into the architecture. Restorative capacity dictates the strategic placement of supply depots and repair ships. Finally, adaptive capacity governs how the network navigates complex maritime borders. Private tech conglomerates own the physical wires, but sovereign states rely on them for their economic and strategic survival. Because no single nation commands the resources to patrol the entire global ocean, subsea telecommunications defy traditional national security models. Classifying these cables as critical infrastructure provides the necessary legal framework to balance national security mandates with commercial realities. True national resilience is achieved when a state accepts that its digital lifelines will eventually be severed. Success relies entirely on engineering the legal, physical, and diplomatic scaffolding required to ensure society survives the cut.